The last topic I want to discuss in this section is going back to this term, the binomial coefficient. So when we're looking at combinations, we had this notation here for n choose k, choosing k items out of a total pool of n options without regard for order. And we mentioned along the way that this is called the binomial coefficient. And I said I would come back to this and talk about why it's called the binomial coefficient. There's a lot of sort of interesting things. This is mostly sort of side interest, although you will see a couple of homework questions that ask you about this. But there's a lot that you could take this and run with it, and you'll see some interesting ideas here. So the question is, why is this called the binomial coefficient? So let me set this up with an example. If you want to expand something like x plus 1 squared, so this is a binomial because there are two pieces added together, so binomial, two pieces, and then we are raising that to a power. So we're multiplying out a binomial by itself. And of course, you know how to do this. You would FOIL, or whatever you want to call it, although I don't like the term FOIL, but you would expand this out and you'd get x squared plus 2x plus 1 after you combine like terms. So in general, there's a formula for this, of course, that a plus b squared is a squared plus 2ab plus b squared, right? So that's the familiar piece. Then if you wanted to cube this, well, it gets tedious, but if you worked at this and if you expanded it out, you could take a plus b squared and then multiply that by a plus b again and do all the distribution, collect like terms, and so on. It would be tedious, but what you'd eventually get would look like this. You'd have a cubed plus 3a squared b plus 3ab squared plus b to the third. Okay, so far so good. Then if you raised it to the fourth power, this would be even more tedious, but if you work this out, you'd get a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab to the third plus b to the fourth, which may not look like much yet, but let me show you one more entry here at the risk of being tedious. We can write down all these terms. And what we're looking for is a pattern here. The pattern may or may not be obvious, but I can write this down by just writing down these coefficients. We can start to notice an interesting pattern. And if you keep on going, eventually you can get to something called Pascal's triangle. So Pascal noticed this interesting pattern, and it turns out there are all sorts of really curious things about this pattern. So let me start writing down Pascal's triangle. So Pascal said if you start with a 1, and then a 1 and a 1 like this. And then if these diagonals here, you just keep filling in 1s, this would look like, if you go along here, all of these coefficients are 1s, and all these coefficients are 1s at the far ends. So that continues on. And then between those, each number here is the sum of the two numbers above it, to the left and to the right. So if you take, for any entry here, you take the number up and to the left and the number up and to the right and add those together, notice that what you get here is the coefficients of this binomial expansion. If we keep on going, if we build the next row, the outer entries would again be 1. This number here would take the 2 and the 1, added together, it would make 3. And then the same thing on the other side. Notice that those are the coefficients right here, 1, 3, 3, and 1. And if you continue doing this, you notice the next row again has 1s on the outside, then it's 4, 6, 4, and again that looks like the expansion of a plus b to the fourth. And you keep on going and this pattern continues. There's all sorts of interesting conclusions to this, which we won't talk much about, but I will say that some students in the past have done their final presentations on topics that come out of Pascal's triangle. There's lots and lots of interesting results that come out of this, lots of interesting patterns that you can follow. So if you're looking to expand a binomial, if you know how to draw Pascal's triangle, you can quickly recreate this and then pick out the coefficients. So when I wrote down these answers up here, I didn't bother actually doing the algebra to simplify them. I just jumped straight to the answer by knowing this approach with Pascal's triangle. So just to show you the details of this, it helps to sort of number these starting at 0. So this would be row 0, this would be row 1, row 2, row 3, etc. And the row corresponds to what power you have on this expansion, at least as it relates to that. So row 2, for instance, has the coefficients for a plus b squared. Row 3 has the coefficients for a plus b cubed. Row 1 would have the coefficients for a plus b to the 1, which of course the coefficients would both be 1 and 1, which makes sense. So the rows start at 0, and then within the row you have the entry also starting at 0. So this, for example, would be row 4 and the first entry. Even though you might say, well, that's the 5th row in the table and that's the 2nd entry in, since we're starting counting at 0, this ends up being row number 4 and entry number 1, where this would be entry number 0. Now, why is that significant? It turns out that that 4th row and first entry, the value is equal to 4 choose 1. Over here, this would be the 5th row and the 3rd entry, and that's equal to 5 choose 3. Notice, by the way, it's also equal to 5 choose 2 because the same value is over here. But again, knowing this, if you're working with small enough numbers, you can just read off from Pascal's triangle the value of a combination problem. So there's lots of curious things in this triangle, which I'll show you a little bit more in a second. But first of all, you'll notice that there's what's called the Binomial Theorem, which basically is a formula for how to expand a plus b to the n. So it says a plus b to the n is equal to, you're going to have, leaving a little space, you're going to have a to the power of n as your first term, and then each subsequent term, if you notice the pattern here, each time a goes down by a power of 1. So it goes from the 5th power to the 4th to the 3rd to the 2nd to the 1st, and then lastly to the 0th power, so it disappears. So following that pattern, the next term is going to have a to the n minus 1, the next term is going to have a to the n minus 2, and so on. And then the powers of b do the opposite. So a reduces in power 1 each time, b increases in power from b to the 0 to b to the 1, b to the 2, b to the 3, and so on. So you'll have a b here, then b squared. Then if you keep on going, you would have b to the 3rd, and so on. At the end of all this, the last term is just going to have b to the n and no a's. So notice, by the way, that the powers here are always going to add up to n. So n minus 1 and 1, n minus 2 and 2, and so on. So there's a lot of interesting patterns here. Then the coefficients of all these terms are going to be, it turns out, this choosing or combination answer. So for a to the n, the first term is going to be n choose 0, which it turns out is always going to be 1. Because if you think about how many ways are there to select nothing out of your entire group of n, there's only one way to do that, just to select nothing. Then the next term would be n choose 1, then n choose 2, and so on, all the way until the last term, which will be n choose n, which again is 1. If you think about how many ways are there to select all of the items in a group, there's only one way to do that, to select all of them. So the shorthand for this, and if you haven't seen much of this series notation, then you don't need to worry too much about this. But if it helps, this looks like the general term n choose k, and then a has the power of n minus k, and b has the power of k. And what this series notation says is start with k equals 0, that's your first term right here. Then move k up to 1, that's your next term. Then move k up to 2, and so on, and then add together all of those results. So this second line is just a shorthand way of writing down that first line, the exact same value. So there's the binomial theorem. But really quick, just going back to Pascal's triangle, there are a couple of interesting things, patterns that you can find in Pascal's triangle. There are all sorts of curious natural phenomena that find their values or their patterns in Pascal's triangle. But let me show you one, just briefly, one simple pattern that you may find interesting. And this kind of comes from number theory, just looking for interesting patterns in numbers without worrying too much about applications or anything like that, just looking for interesting patterns. It turns out that if you look carefully, this at the diagonals really is what's interesting. If you look at these diagonals right here, so this first diagonal, if we continue building another row or two, just to keep filling this in, all right, that's probably enough. If you look at that first diagonal, you can see it's 1, 2, 3, 4, 5, 6, 7, and it's going to continue on. That's just the natural numbers. So the natural numbers are sort of hidden within Pascal's triangle. If you look at the next diagonal, 1, 3, 6, 10, 15, 21, that may not look like a familiar pattern at this point. But if you look carefully, what's happening here is it's really the sum of the numbers up to a certain point. So this is when you add up just 1 by itself. This is when you add 1 and 2. This is when you add 1 through 3, then 1 through 4, then 1 through 5, 1 through 6. And the name for this, we've talked about, I think, briefly before, but these are called triangular numbers. Now, why are they called triangular numbers? The idea is that you can draw a triangle with that many dots. So let me show you what I mean. So 1 just looks like that. Doesn't really look like a triangle, but 1 or a 3, the next triangle, you can draw a pattern like this. And if you add another row below it with 6 dots, now you've added a row with 3, you have another triangle. If you add another row below that, it would need to have 4 dots in it. That would look like that. So there's 10. Another row below that would need to have 5. And so that's a total of 15, and so on. And so the number of dots in each of these pictures is following this pattern of these triangular numbers. The next row is even harder to see. That's a much harder picture to draw, but it turns out that these are called the tetrahedral numbers. And you may know what a tetrahedron is, or you may not, but a tetrahedron is roughly a 3-dimensional equivalent of a triangle. I'll try to draw one here, and it won't be very good, but basically if you start with a triangle as your base, and then you pick another point above it and draw down from that point to the others. So it's basically a pyramid with a triangular base. That's roughly what a tetrahedron is. So that's a tetrahedron, and notice that we've got 4 dots there. If we built the next level up, it would have 10, and then 20, and then 35. So these grow much faster because we're working in 3 dimensions. If you're interested, the next ones are called the pentatope numbers. It turns out these are roughly equivalent to 4-dimensional triangles, which I'm certainly not equipped to draw. Nobody is, right? And then the next row would be like 5-dimensional triangles and so on. So there's lots of interesting patterns, and we've barely even scratch the surface, but there's lots of things within Pascal's triangle that are very, very curious, interesting patterns you can find. So if you're interested, you can look up more on Pascal's triangle and you'll find lots and lots of interesting things to learn from it.